Can you see the screen?
Yes, sir. Visible, sir.
Okay. Okay, and I'm Minoru Kuribayashi from Tohoku University, Japan. And today the title is Secure Embedding, Data Hiding for Privacy-Sensitive AI. So basically, my talk is related to the data hiding for AI models, but it is also related to the protection against the illegal copying of the DNA models. So not only the data hiding, but also the management of the AI models is the main topic of today's talk. Okay. Okay, this is the agenda of today's talk. First, I'll explain about the background of this talk, and then we introduce DNA watermarking and DNA fingerprinting. These two terms are slightly similar, but strictly it is different. So I explain about the difference of these two topics and explain about the detail of the techniques. Then we move to the ownership verification process based on the watermarking and the fingerprinting. And also consider about the countermeasure to realistic threat. And then move to the other topics like proof of training. It is a kind of the proof of the DNA models training process. Okay, finally, I'll conclude this presentation and talking about some future works related to this topic. Okay, at first, as you know, deep neural networks are very widely used in the real-world applications, such as image recognition and cloud-based AI services. But it also arises a new threat, like let's say, infringement of the intellectual property of the AI models. So these models may be illegally copied and deployed at the cloud servers. So it is a threat in this recent environment. So for example, here is the owner, and the owner will try to develop AI models. Then the malicious party will steal the model in a certain way, and then the stored model is deployed at the cloud server. So in such a case, the owner want to claim the intellectual property of the original model, but the malicious party will try to defend against the ownership verification by the owner. So this is a dispute against the owner and the malicious party. So we try to protect the intellectual property of the AI models. But in the real world, there are another trend, like open source software. So it is a computer software that released under a license in which the copyright holder grant users to right to use, study, change, and distribute the software. And the source code can be modified in any purposes. So one of the examples is OpenAI. OpenAI is producing some software like pre-trained AI models to the everyone. So everyone can easily downloading from the pre-trained from the OpenAI server. And then the pre-trained AI models can be modified according to the user's interest. So there are two directions of the development of the AI models in the world. But in this case, the open source, even if the open source software is very active trends in the world, there's also the other trends like a subscription-based contract. So if you want to use the services as a online or cloud server, you need to pay the money to use that models. So for example, in ChatGPT, you need to register and pay the money to use the reliable AI model. So in this sense, the open source software is one direction, but the protection of the model is still requires in the case of the subscription-based contract. So in this sense, it requires the management of the AI model ownership. Okay, now let's move to the second topic, DNN watermarking. So what is watermarking? Maybe many of the audience of today's talk will familiar with the DNN digital watermarking? No? I'm sure. Okay, anyway. So the digital watermarking is a technique to embed a sub-information into multimedia contents like music, photo, video, and so on. And it is possible to insert a sub-information without seriously degrading the quality of the multimedia contents. So this slide shows an example. This is the original image, and the owner want to embed the watermark information like this B, and using the certain algorithm embed. Then as a result, it outputting the watermarked contents. So in this content, it involves the sub-information B. So if the watermark is extracted from the suspicious copy, the owner can claim the ownership of the image. So this is a typical model of the digital watermarking. So what about the watermarking for the DNN model or AI models? So the model is that analogy to the conventional digital watermarking. So in this case, here is the AI model, and the model is input into the certain embedding algorithm, and the sub-information B is embedded using the algorithm. Then as a result, the AI model involves the sub-information, the watermark information. So the difference from the multimedia contents, the AI models consist of several network layers and a large number of weight parameters. So the candidate to embed the watermark information into the AI models is such architecture and its parameters involved in the model. So this is the candidate. And also, as you know, there is a very high level of freedom because the architecture is very complicated. Therefore, we can easily modify the architecture slightly. And also there are a huge number of parameters. It is possible to slightly modify the parameter according to the watermark information. Okay, this slide explains about the requirements for DNN watermarking. And in this slide, I enumerating 4 requirements. One is the robustness. And robustness is tolerance against attacks. So in the case of multimedia contents, the watermarked contents will be modified by the malicious party to remove or to change the embedded watermark. So in the case of DNN watermarking, it is also required to tolerate for various attacks. And the attacks is really different from the original digital watermarking for multimedia contents. So in the DNN model, the attacks is like a model fine-tuning, model pruning, distillation, and so on. So such a modification of the DNN model is a typical case of the attacks for the DNN watermarking. Okay, the second requirement is the fidelity. So the presence of the watermark does not degrade the quality of the watermarked object. So this is a typical requirement for the digital watermarking for the multimedia contents. So in the multimedia contents, the quality of the content should not be degraded. In the case of DNN watermarking, the AI models should not be degraded to the performance of the original task. So this is the fidelity required for the DNN model, DNN watermarking. And the third one is the capacity. It is desirable to embed more information into the model, right? But it is very sensitive issues in this case because there is a trade-off among robustness, fidelity, and capacity. So the balance between among these three requirements is very important. So if you want to increase the robustness against attacks, the capacity will be becomes small. Okay. The fourth one is the security. And adversary will try to replicate the functionality of the target model, like a distillation of the AI models, to create a surrogate model, right? So even if the model is copied or to extracting certain functionalities of the model to create a surrogate model. So in such a case, the watermark should be survived even in the surrogate model. So this is a security requirement. This slide shows a typical example of the convolutional neural network architecture. So this is an input image, and in the convolution layer, it tried to extracting the some feature element from the input image using the convolution, pooling, batch normalization, or something others. And finally, it extracting a certain feature element from the input image. Then, using the fully connected layer, the feature element extracted from the original input image, it's classified into a certain classes. So there are some labels of the classes. Then it output the probability according to each class. So the output could be a softmax function. So it means the probability of each classes is outputted as a logic. Now, based on this architecture, we think about the preliminary works of the DNN watermarking proposed by Uchida et al. In 2017. So in the ICMR conference. So in Uchida's method, this is an AI model, and this model will be trained to outputting according to some original cost function E0. So this cost function is a parameter, is a measurement. The output from the AI model should be close to the correct output. So the difference between the output of the AI model and the correct output is calculated, and the difference is measured as a cost function. So in the training phase, the weight parameters in the AI models, the DNN models, are updated to reduce the difference between the output and the correct level, correct output. So in the case of watermarking, some parameters, some weight parameters are extracted, and then calculating the product of secret matrix X, and the output is produced. And in this case, the output should be close to the watermark information. So this is a watermark sequence. So the output should be close to the watermark. Then it introducing the embedding cost function. So in the training, the weight parameters is modified or to updated to satisfying the difference between these group parameters and this watermark sequence is close to each other. So the difference is should be 0. So this is a embedding cost function. And in the Uchida's method, it introducing two cost functions, E0 and EW. E0 is the cost function of the original task, and EW is the cost function for the watermark embedding, and lambda is the control parameter. So by using this cost function, the AI model is trained. Okay. So this is the original idea of the Uchida et al.'s method. So the effect of the embedding watermarking in the training phase can be interpreted as a following explanation. So at first, we think about the local minima and the global minima. So it is well known that the deep neural networks have a lot of parameters. Therefore, it has many local minima. And the local minima are almost optimal. So, I mean, in the feature space, and there are some local minimums. And this one is a global minima. And in the training of the DN model, at the training from scratch, the initial point is randomly assigned. Then, using the training phase, the initial point is moved towards to a certain closest local minimum. Of course, it's better to find the global minimum, but we do not need to find the global minimum. In the training of the DNA model, the initial point is moved towards the closest or one of the local minimum. So it is sufficient to find the local minimum because the performance is almost optimal, very close to the global minimum. So this is a training of the original task. But in the case of watermark embedding, it introduced in the training phase, then the process is already modified from the original training phase. Okay. So this is the original point and try to find the one of the local minimum. Then to embed the watermark in the original training task, the initial point is moved towards a certain direction. But by introducing watermarking operation, watermark embedding operation, it slightly modified the vector to the other direction. So as a result, the training plus watermarking will be moved towards this direction, for example. So then, after some epoch, this training phase will be convergence to a certain local minimum. As you can see, without watermarking, the initial point will very easily convergence to a certain local minimum. But even if the watermarking is introduced, the training is finally convergence to a certain local minimum. Therefore, the effect of the watermarking does not affect the training of the AI model in this case. Okay, and this slide also show the other approach of DNA watermarking. It do not require the embedding loss function, so embedding cost function. So the embedding watermarking can be regarded as a move to the initial point to the other point. So this is the original initial point. And after the watermarking, the initial point is moved towards the other point. So this point is some dependency of the watermark information. In this case, so the model is trained using the original cost function, and some parameter is sampled from the model. Then the watermark weight parameters is produced, then replaced with the original weight parameters. So just only doing this operation. But in this case, the selected weight parameters should be fixed, because for each epoch of the training phase, the weight parameters of all of the parameters will be updated. So it means the embedded watermark into the selected weight parameters will be modified. Therefore, the only requirement of this watermarking operation is at each training phase, the changes of the models of the weight parameters at each epoch is corrected to satisfying the watermarked weight parameter. By doing this, the watermarked weight parameter is still keep the original watermarked weight parameters. Okay, so for each epoch, the watermark is embedded to satisfying the watermarked weight parameter. And the AI models is trained using the cost function E0. Without the embedding loss cost function, it is possible. So the reason why is during the training phase, the changes of such weight the weight parameters is corrected at each epoch. So this slide also shows the mechanism of the watermarking without embedding loss. So in the original training phase, at each epoch, the weight parameters are updated at the first epoch, second epoch, third epoch, and so on. So the weight parameter is updated until a certain iteration of the epochs or certain condition is satisfied. But in the case of DNA watermarking without embedding loss, the embedding operation is performed just every after the epoch. So in this case, as a first epoch, it can be regarded as the initialization of the DNA model. So it means the initial point is moved towards a certain different initial point. So at the first epoch, it is the initialization. So the initial point is moved towards a certain different initial point related to the water information. Then after the first epoch, the second epoch, all of the parameters will be updated. Therefore, using in the embedding operation, it corrects the changes caused by the training at the second epoch. Then third epoch is updating the weight parameters. Then the embedding operation will correct the changes. So by using these operations for each iteration of the epochs, the embedding of the watermark is still kept. Okay, this slide shows some numeric as an example of the convergence of the training. So as you can see, at the first epoch, the mean square error of the weight parameters is very large, because at the first epoch, it moves the initial point towards the other initial point. So it's causing the big difference of the weight parameters of the original AI models. But after the first epoch, at the first epoch, at the second epoch, the weight parameter is updated, and only for the sampled weight parameters and its changes are corrected in the second embedding operation. Therefore, the mean square error of the weight parameters becomes small. Maybe you can see the scale of the y-axis is a long scale. So the amount of the changes is very small. Okay. So at the first epoch, the changes of the weight value is very large, but it can be regarded as one of the initialization operation. And after the second epoch, the changes of the weight values convergence without the embedding loss function. So it is the advantage of the DL watermarking without loss function. Okay, this slide also shows the effect of the following phases of the embedded watermark. So as you can see, there is no clear difference of the accuracy and loss function. So therefore, the embedding watermarking during the training phase do not affect the performance of the training. Also, the finally trained models. So there's no significant difference between these original model and the watermarked model. Okay, now we move to the other perspective of the DNA watermarking. So there are two possibilities of the owner of the model. So in the white box setting, the owner can access to the internal structure of AI model or internal weight parameters. So it means the full access to the internal structure of the AI model is allowed for the to the owner. So therefore, the watermark is embedded into the internal weight parameters of the AI models, and in the case of illegal copy is found, the owner tried to extract the watermark directly from the AI model and claim the ownership. In general, it is difficult. As you know, the illegal party, the malicious party, will try to defend, will try to protect their model, their stolen model, right? So this white box setting is very realistic situation. But in general, it's difficult for the owner to full access to the internal structure of the AI model. So in the realistic situation, the black box setting is much more realistic. So it means the owner can access to the AI model but can use the AI model. For example, the AI model is deployed as a cloud server. In such a case, the owner try to throw a query to the cloud server and receiving the result. Then only input and output pairs is observed. So according to the input and output pairs, the owner tried to check the model contains watermark or not. So in such a case, the owner tried to prepare a certain trigger input. Then the trigger input is input to the AI model and receiving the output. Then if the output show a certain irregular behavior, then the owner can claim the model is watermarked. So it means the owner embed watermark into the AI model, but the watermark itself is a kind of the backdoor. So a specific input is received the AI model with outputting a certain irregularity. So one of the example of the output is a logit. So in the image classification task, this image is input to the AI model. Then the output could be the probability for the class, for example, cat, could be higher, and the other classes, the probability should be lower. This is the logic. The probability, the sequence of the probability show a certain irregularity. Then it show a certain backdoor. So the AI model is reacted to a trigger input of the image. So the owner can claim this model is watermarked. So this slide shows the example of the ownership protection, the watermark, the restriction of the watermark verification process. So here is the owner, and here is the malicious party. The malicious party deploy a stolen model at the cloud server. And the owner will suspect the model in the cloud server could be my model. Then the owner tried to check. In this case, the owner cannot access to the internal structure, like architecture and parameters, but he can throw a query and receiving the response. So this is a realistic situation. So the owner will try to throw a query and receiving the response. And according to the response, the owner tried to convince the model in the cloud server could be a stolen model of his original model. So in a black box scenario, the owner will embed the ownership information into the AI model during training, and it enabling it to output an identifier when a trigger input is provided. So this is the trigger input, then through query and receiving the result, it shows a certain identifier. So the AI model will outputting some irregular output. So the irregular output is related to the identifier. If the irregular output is observed from the response, the owner can convince the model is stolen one. However, in this scenario, there are some drawbacks. So the watermark in the AI model will affect the performance of the original task because the owner will make some backdoor on the original model. Therefore, a certain special input is reacted. Right? The AI model is reacted to the certain special input. Therefore, it is a backdoor of the AI model. So such a backdoor will affect the performance of the original task. And also, the number of trigger input should be determined in advance, right? So to make a backdoor, the owner tried to train the model. So only for a set of trigger input, it outputting some irregularity. So it outputting an identifier. So the owner tried to train the model according to some finite number of the trigger input. So this is a drawback of this scenario. Okay, now we move to the second techniques, DNA fingerprinting. So in this technique, so it's tried to verify the model identity by extracting the model specific information. So the owner do not embed the watermark into the model. Instead, it tried to extract a model specific information. One of the example is a decision boundary. of the image classifier. So for example, here is a feature space, and this is a feature space, and some points are classified as a class A, and some are classified as a class B. And this red line is a decision boundary. So the owner tried to create some examples close to the decision boundary, and the owner tried to throw a query to the cloud server and to receiving the result. If the decision result of some samples are classified as class B or class A, then he can find the decision boundary. So by throwing some queries, he can find the model's decision boundary is very close to his original model. Then he can claim, the owner can claim the model installed in the cloud server could be similar to his original model. So this is the idea of the fingerprinting. So in this case, there is no operation of the watermark. The watermark is embedded into the model. Instead, it tries to extract model-specific information. So this model-specific information is checked by the query and response challenges. So now we think about how to find these samples. So these are decision boundaries. How to find these samples is difficulties of this task, of this technique. So one of the approach to find the samples can be produced by the adversarial attack. Do you know adversarial attack? It is a creation of the tiny noise to cause misclassification of the image classification task, image classification AI model. So, for example, this is a original image. If this image is input to the AI model, then it's outputting panda. It can be classified as panda, as you can see. But if a certain perturbation, the noise, is added to this image, then for human eyes, it is still looks like panda. But the DNA model, the AI model, will outputting gibbon by mistake. So this is an advanced example. So this is the difference between the human eyes and the machine eyes. Machine eyes are more sensitive to the adversarial perturbation. So it means one example, one original image classified as panda can be moved to the other class by adding noise. So in the class of the gibbon. So it is possible to make two samples between the decision boundary. So in the DNA fingerprinting, using the advanced examples, the owner try to create an advanced example using the information of the input image and the original model, then creating the advanced example. So this advanced example is thrown as a query to the cloud server and receiving the response as an identifier. So by iteratively making the query and response, the owner can convince the model is deployed by storing his original model. So this is a mechanism. This is the idea of the DNA fingerprinting. But maybe you can find some analogy of the DNA watermarking, because in the case of DNA watermarking, a certain information, watermark information, is embedded to create a watermarked image, right? So this is the original image, and this is a kind of can be regarded as a watermarked image. But in this case, the embedded information is not a watermark, but the adversarial noise. So, but there's a certain level of the analogy of the watermarking and the fingerprinting. Okay, and now move to the categories of the adversarial attack. So this is the original image and this is the AI model. So it will outputting a certain scores for each classes. So for example, in this case, it can be regarded as cat. So this class is cat and dog and monkey and something. So for the probability of the cat class becomes higher. Therefore, the AI model determine this is cat. But if adversary perturbation is added to this normal image, so this adversary example is input to the same AI models, then the output will be changed. So for example, this is a dog. So these adversary perturbations, this noise, can be created in a two manner. One is a targeted attack. So how to change the class, the output class is specified. So the noise is created to misclassify as a specific target class. So in such a case, it is called targeted attack. And the other one is a non-targeted attack. It changes on input to any other classes. So any classes defined from the actual class. So this adversary example can be classified as other than the cat. So this is the case of the non-targeted attack. So in a DNA fingerprinting, it is suitable to using the targeted attack because it is very easy to manage to the decision boundary. So class A and class B. So this is the decision boundary, and this is the input image and original images class. And by adding the noise, this class is moved to the other class. So this class can be specified. It is much more easier to control. So the decision boundary can be easily determined in this case. And also the other categories of the adversary attacks is a white box, gray box, and black box. So this is a little bit different of the categories. In the white box attack, the attacker has full knowledge and access right to the model. So if the model parameters is known for creating the adversary perturbations, such attack is called white box. And in the black box, the attacker has only access to the input and output of the DNA model. And gray box is the middle of the white box and the black box. And this way is much more easier to find the categories of the adversarial attacks. So this is a target model. Then the adversary can observe the model. Then it is possible to make adversary white box attacks. One of the typical attacks is a gradient-based attack. And the other attack is a black box attack. So the owner make a thorough gauge model and creating adversary example. And due to the transferability of the adversary perturbations, the adversary example, it can be worked as a thorough gauge model is also useful to the original model. And the others are also related works. Okay, anyway, this is some categories of adversarial attacks. So in the case of target and transfer based, the advantage is the adversarial example not only fools the attacked model, but also transfer to fool other models sometimes. So it is helpful to make it robust against model modifications, such as pruning and fine-tuning. I mean, in the case of the illegal copying of the model and deployment of the model at the cloud server, the malicious party will try to modify the model when applied to the cloud server. So in such a case, the AI model on the cloud server is slightly different from the original model. Then it has some difficulties of finding the decision boundary in the case of the DNA fingerprinting. But in the transfer-based attack, the transferability of the adversarial perturbation becomes helpful to make it robust against model modification. So model modification means malicious party will try to modify the model so that the ownership verification of the model in the cloud server it becomes difficult. So, but if the transfer-based attacks is possible, the transferability of the model is make it more robust against the model modification. And the other approaches is the transferable adversarial examples. So in this case, so these are the original image, and this is adversarial perturbations, and this is adversarial example. Okay. And the source model is the original model, and salvage model is a kind of modified model from the original. So if this adversarial example is input to the source model or salvage model, then it can work correctly. Correctly means adversarial examples is reacted to the model. So this image is horse, looks like horse, but it is misclassified as car. And this one is this is original image is truck, but it's misclassified as frog. And this is like I think dog, but this is classified as airplane. So the adversarial example can work correctly to fool the model. And in the case of surrogate model, the model is slightly modified from the original. Then this adversarial example is still worked correctly. So it means the output will won from the original level. On the other hand, the reference model is completely different model. There's no relation to the original model. So this is just a different model. So in this case, the model can outputting the correct labels, horse, truck, dog, horse, truck, dog. So the output could be same as the original task. So this is the kind of the comparable alpha examples. So like targeted transferability occurs only from the source model, original model, to its surrogates, but not to independently trained different models. So this is a requirement. This is a important features for employed in the DNA fingerprint. Okay, now I move to the fourth topic, the ownership verification process. So I have explained about the DNA watermarking and DNA fingerprinting. It enables an owner to claim the model deployed in the cloud server will be his own model, will be illegally copied from the owner's original model. But in this scenario, the owner only discover the suspect model as a cloud server, and the owner can verify the identity of the AI model. But for the requirement for the ownership verification, it also necessary to demonstrate the possession of the model to the third party. So it means the owner should prove the possession of the model to the third party. There are two steps. At first, the owner discover and try to check the model deployed on the cloud server will be the illegally copied model. This is the first step. And the second step is to prove to a third party. So this is a very important requirement for the ownership verification. And the second one. Okay, so the first one is a check of the suspect model in AI as a service. So in this case, the model is deployed as a cloud server. So in such a case, the owner cannot have access to the internal structure of the AI models. Therefore, the black box access the suspect model. But once the owner prove to the third party of the illegal copy of the cloud server, the third party will request for the model access to the cloud server. So the manager should submit the model deployed in the cloud server, and the third party will try to check the ownership by extracting the watermark or the record of the blockchain, for example. So there are some level of some steps for checking the ownership verification. So in the second step, it is like a law enforcement. Once a third party convinces the model is copied, the verifier, the third party, will try to make a law enforcement to access to the model in the cloud server. But this is just a second step. In the first step is very important factor in this case. So black box access to the suspect model, and the owner should prove to the third party. So this process is very important point. So it means the owner will find a suspect model at the cloud server. Then at the first step, the owner try to identify the suspect AI as a service and try to make through a query and receiving the response. Then the owner convince the model in the cloud server could be a copied model of his original one. Then the owner in the second step prove the fact to the verifier. Then the verifier is convinced. The verifier requests the submission of the AI model in the AI as a service based on the law enforcement procedure. Okay. This is the natural process of the law enforcement. So without this process, it is difficult for the verifier because the owner may frame innocent AI as a service manager. So it is obligate for the owner to prove the fact of the illegal copy of the original model. So malicious party may actively monitor. In this case, at this step, the malicious party will try to protect this process because the malicious party may actively monitor the input and output of the deployed model. So maybe the owner will creating a trigger input as an advanced example, then throw query and return the response to the owner. In this case, the malicious party can observe the input from the owner and try to check the output from the AI model. If the malicious party finds there are some irregularities, then the malicious party will reject the queries from the owner. Right? So in this sense, it is necessary for the owner to avoid triggering anomaly detection during the ownership verification process. So this is a threat model. So here's the owner and malicious party, and malicious party will try to observe the input and output of the AI models. And if there are some irregularities arise in the can be found, the owner will try to reject the queries from the owner. So this can be regarded as a stealthiness of the ownership verification process. Okay, in the conventional DNA fingerprinting, it using the adversarial attacks. But in the conventional adversarial attacks, it only changing the output of the AI model by adding the noise. So, for example, in this case, the cat class becomes higher probability in the normal image. So this correct class probability becomes very high probability. By adding noise to creating the adversarial example, then, for example, the dog class becomes higher, and the correct class, the cat class, becomes lower. So in such a case, if the input and output is observed by the malicious party, oh, it seems very strange. So the malicious party will notice the owner will try to make a verification process. So this is a violation of the stealthiness. So to solve this problem, my group proposed a new adversarial attacks. It can control the probability. So this is a normal image and outputting correct label, correct classes. And in the case of adversarial example, it outputting this specific output. So the original correct class probability is still higher, and the target class is slightly increased. So this probability can be controlled so that to keep the stealthiness of the adversarial example. So for the malicious party, it is difficult to find the input is strange, or the output is strange. Maybe it is difficult. So it's difficult to detect by the malicious party, the cloud server's manager. This slide shows the numerical comparison of the conventional adversarial attacks and the proposed adversarial attack. In the case of the conventional adversary attack. At the first, before the adversary attack, the correct class is like a probability is 0.4, and the target class is very close to the 0. But after some iteration, the target class probability becomes very high, and correct class probability becomes very low. So in such a case, it is very easy for the malicious party to notice the input image. The input is adversary example. But in the case proposed method, the correct class probability is still dominant. The top one class, higher probability, but the target class becomes higher. So in this case, the probability of the target class is controlled by giving the restriction 0.3. So by some iteration, we can control the output of the target class. It's close to the 0.3. So it is possible to control the probability of the adversary examples. So this slide also shows the other examples. So in this case, the target class is only one class, but it can be increased 2 class or 3 class. So it is possible to extending to the multi-class. Now we think about the zero knowledge proof. Zero knowledge verification process. So the owner should prove the model ownership to the verifier without presenting the original model. So the owner should prove the verifier without presenting the original model. So in this protocol, the verifier throw a request to the owner. This is the input image and target class and its probability. Then the owner tried to create the adversary example. So because the owner has a full access to the original model, he can accurately controls the output. This is a target probability. So target class and target probability. And this is original class. So it is also still dominant probability. Therefore, the top one, this adversary example can be classified as original class. Okay. Then the owner answers the adversary examples as a result to the verifier. Then the verifier throws the adversary example to the cloud server and receiving the result. And if the result is close to the requested target class probability, then the verifier convinces it is determined as identical. Okay, this slide shows some simulation result. The left one is the difference between the probabilities. So the verifier through a query to the cloud server and observing the result, and this is a target probability and target class probability, and its target probability is very close to the specified ones. Then the distance between the observed signal and the received signal. So the distance is close to 0, it means it's identical. If the distance is larger, the maximum is 1.0. If the distance is 1, it is completely different. Okay, so this graph shows the original model, like a ResNet, and different version of the ResNet and the VGC network. And this is cloud service net, models. This ResNet 18 is deployed and stolen by the ResNet 18. Then the distance becomes close to zero, and close to zero, close to zero. And the if the model is different, the distance is very longer. Therefore, if the if the model is so the owner's model is same as the cloud service model, then the distance becomes smaller. If the model is different from the cloud service model, then the distance is larger. So only when the distance is close to the only when the model is same, the owner's model and the cloud service model is same, then the distance becomes smaller. So as a result, this result shows in the case of the model verification, the owner can convince the verifier. And now we also think about the countermeasure to the realistic threat. So in this case, the AI model modification such as retraining and fine-tuning. So the malicious party will try to modify the original model before deployed as the cloud server. So in such a case, it becomes difficult for the owner to convince the verifier because of the threat modification of the model. So I mean, the adversarial perturbation is not always valid to the different version of the model. But in this case, there's a restrictions. Original model is slightly modified. In such a case, the model is still identified. Okay, this is one of the threat. So the requirement is even if the minor modification is performed before the deployment of the cloud server, the ownership verification can work correctly. And the other thread is that adversarial perturbation are sensitive to denoising process. So it means this is the original image and adding the adversarial perturbation to creating the adversarial example. But if the adversarial example is compressed by JPEG, like a lossy compression, then the effect of the adversarial perturbation may be degraded. So therefore, it is necessary to make it robust against the denoising processes. Okay, this slide shows the robustness to retraining. So it means a minor modification. Some model is retrained before the deployment of the quad server. So in this case, retraining, the distance of the let's see, yeah, the verifier gives the target class probability, and adversarial example is thrown to the class server and observing the result. Then the distance between the target class probability and the output probability. So in this case, the target target class probability is set to 0.3, and by making the retraining, it is a little bit fluctuating. But so in the increase of the retraining epoch, the fluctuation amplitude becomes larger. But even in such a case, the mean of the target class probability is still close to the predetermined probability. Therefore, it is still possible to make the ownership verification in this case. Okay, and second one is in the case of JPEG compression. There are scenarios. The owner will try to create an adversarial example and compress the image by JPEG at the owner side. Then through a query to the cloud server. And at the cloud server side, the malicious party will try to compress the received image by JPEG again, so that the adversarial perturbation will be removed. So it means at the first it is compressed by JPEG, and at the cloud server side, the image is also compressed by JPEG. So this is a kind of the double compression scenario. So this image is input to the AI model, then outputting the result. Then Mr. Party also observing the process of this operation. The input and output can be observed. Then return to the response to the owner. So this is a scenario of the compression. So in this case, the owner knows the quality factor of the JPEG as a owner side compression. But as a cloud server side, it is unknown. The quality factor is unknown as a JPEG compression as a cloud server. So in this scenario, the owner tried to adjust the adversarial perturbation to make it robust against the double JPEG compression. And the first compression, the quality factor is known, but the second case, the quality factor is unknown. So this slide shows the compression-aware adversarial attack. So the owner may apply lossy compression before transmission. So therefore, the owner tried to create the adversarial perturbation according to the effect of the lossy compression. So this is a quality factor, and this is also generation quality factor. So as a quality factor is known in advance, the adversarial example can be crafted to keep the probability control capabilities. So it means if a quality factor is known in advance, it is possible to create an adversarial example that can satisfy the predetermined probabilities. So the output of the AI models can be controlled. So, but the owner only know the quality factor as a first JPEG compression. The JPEG compression as a cloud server, the quality factor is unknown. So it is difficult for the owner to get the information about quality factor in this scenario. But the owner tried to estimate the quality factor by by making the iterative query and response trials. So this is the result of the query and the response trials. A little bit difficult to observe, but anyway, in the storm model, the owner tried to make a changing the quality factor, and okay. So owner tried to create an advanced example, considering the effect of the JPEG compression. And through query and receiving the result, then the result is a little bit different from the estimated ones, from the assumed ones. Then the owner tried to change the quality factor. So by making some iterative query and response trials, the owner tried to estimate the quality factor at the cloud server side. So by iteratively through queries, the owner can estimating the quality factor, and as a result, if the cloud server's quality factor is 70 to 95, then the probability. So that means adverse examples probability can be controlled by using the estimated quality factor. But in the case of the difference model, so the model is completely different from the stored model or the original model, then it is difficult to estimating the quality factor. And so the owner cannot adjust the probability to the different model. Okay, now we move to the other topics. It is a kind of proof of training. So this is the ideas of the deep learning proof. So the owner will try to train the model as a GPU servers, and during the training, the training records are stored so that the owner can claim afterward. So he has a trained model as a result, but he also store the process of the training as a proof of learning. So this is the idea of the original task. It's proposed in 2021. So the training record is stored. And using a training record, so this is the original model, the scratch model from scratch. Then updated as the first epoch, then second epoch, third epoch. So the model weight parameters is updated at each epoch. So if the training record is stored like a information, the data instance information and some auxiliary information and signatures, then it can be reproduced the intermediate weight parameters. So in general, it is a probabilistic process to update the model weight parameter. So in general, it is difficult to reproduce the same weight parameters. But to make it possible to reproduce the similar weight parameters, it stores the information for updating the model. So for each epoch, it is updated, and using the certain information, it can be updating the similar model parameters. So by doing so, the owner can show he is the trainer of the model, right? Because he has some record of the training. So this is the idea of the proof of learning. So in this case, the verifier will request the owner and the malicious party Okay, this is kind of the second step. The owner convince the verifier at the first stage. He proved the original model and the query service model is same or similar. So then the second step, the verifier make a law enforcement to reveal the model of each party. So in this case, the verifier requests the owner and the message party for the training record. If the owner is a valid owner, he stores the training record. Therefore, he can show the valid training record to the verifier. But for the message party, the message party do not train the model by his side. He just stole the model from the owner. Therefore, the message party do not have the valid training record. Instead, he will forge the training record. But in this case, the message party cannot convince the verifier this is a valid training record. This is a forged one. Therefore, the verifier can check, oh, this is a valid one. This is a forged one. Therefore, the verifier can convince this is correct. This is original owner. Okay. Okay. Anyway, at first, the owner try to check the ownership of the original model by himself by making through a query to the query server. And once he convinced, he tried to prove the infringement of the ownership of his model. Then he proved to the verifier the training record. He has a valid training record. So by this process, the owner can prove to the verifier, and the verifier can convince he is a original model developer. Unfortunately, the original proof of learning has a vulnerability because the proof of learning is vulnerable to the adversary examples. In this case, the proof of learning is related to each other. So this is the original scratch weight parameter is updated. So the owner will store some information about the update of the weight parameters. But this update information can be generated using the idea of the adversary examples. So the detail is omitted in this talk, but the owner can create the valid proof of learning using the adversary examples. Therefore, the original method is not secure against adversary attacks. So instead, Chan et al. Propose ideas of proof of training. So it is a secure proof of training scheme. It can distinguish honest training record from those forged by attackers. So here's a verifier, and here's the honest prover, this is a malicious prover. And the verifier will asks to each of the prover, and if the honest prover shows the training record, it is approved. But malicious prover cannot forge the training record. So this framework is defined mathematically and show an example of the concrete construction of the proof of training in this paper. Okay, And due to the time limitation, I'll skip the details of the method. Anyway, this is the flow of the ownership verification using the DNA fingerprinting. So maybe you can understand the two process. For the ownership verification, it requires the first step and the second step. At the first step, the owner checks the suspect model in the cloud server using the black box access, the suspect model. And the owner should prove the possession of the same model to the third party, to the verifier. Then the verifier will request the model access to the manager and check the ownership by using the watermark or record of blockchain, like a record of the proof of training. So this is a process of the ownership verification. So the ownership verification of AI models are discussed in this talk. The owner has full access to original model, but limited access to the suspect model in the cloud server. So it needs to check the suspect model by query and responses. And in the malicious party, he steals the AI model and deploys it as a AI as a service, the cloud server. And the malicious party can observe the queries and responses to avoid the ownership verification approach. So for the verification, the first step is to check the identification of suspect model. And then it is necessary to prove the fact to the third party. So this is an important factor for the ownership verification. Okay, and this slide shows some future works. So in this talk, I only explain about the very elementary level of the DNA watermarking method and DNA fingerprinting. So there are some spaces for improvement. So to improve the robustness against attacks and to assure the stealthiness of verification actions. So and also some other requirement should be satisfied. And for the ownership verification process, to conduct illegal interpretation and development of ownership protection is required. So to legal interpretation, how to define the legal interpretation of the development of the ownership protection. So maybe the model will be stored and the malicious party will try to modify. Then, how much the difference between the original model is covered? So it's very difficult to define. If the model is completely different from the original, then the malicious party will be regarded as a new developer of the model. But slightly modified from the original model, then such a model, the slightly modified model can be regarded as an illegal copy. So how to define? This is how to draw a line. This is original. This is a modified version. And how to consider the ownership of modified model, such as fine-tuning distillation. This is a very difficult task. So, like a legal interpretation is very difficult to control. Okay. Anyway, in this talk, I explain about the ownership verification based on the DNA watermarking or DNA fingerprinting. And there are some related works and we need to consider about some legal actions, and also let's say it's just it's not just a operation to embed watermark to extracting the model specific information. It also requires some framework of the verification of the ownership. So in this sense, it's very complicated, but it's very worthy of try, worthy of investigate. Okay. So this is the end of my talk. Thank you for your listening.